Okay, today we are starting Unit 5. Today, and most of tomorrow, will be a review of the normal distribution, because that is the foundation for almost everything we are doing for the rest of the school year. Yeah. What you're seeing today, we saw in Unit 1, so hopefully today is familiar ground. We're going to start by talking about continuous random variables. We should know what the meaning of continuous is. We saw it way back in Unit 1. Continuous variables can take values in a specified interval on the number line. In other words, continuous random variables can take on real numbers, integers, fractions, decimals, irrational numbers, anything if it's on the number line, there is a random variable out there somewhere that represents it. Continuous random variable. Yeah. You will notice the specified interval part, because we are dealing with real world variables. There are usually limits on them. If I am talking about the continuous random variable that represents the height of US adults, there is a minimum recorded height for a US adult, right? I'm pretty sure we have not seen a US adult that's only 12 inches tall. There is a bottom limit to how low the recorded human height is for adults. We have a recorded maximum height for humans, right? I should not have a human height that's 32 feet tall. We've never observed a human that tall. So there is a finite range on the number line that a continuous variable represents. It's not the whole number line. It's a realistic part of the number line that corresponds with what we are doing or looking at. Yeah. Hopefully, we also remember that continuous random variables show up when we are measuring something. Discrete variables come from counting. Continuous variables come from measuring. I gave you an example, height of US adults. I would like you to take about 60 seconds in your small group and come up with some other examples of possible continuous random variables. Bonus points for creativity. Second period holds the mark for that for right now. Third period could not beat them. 60 seconds. Continuous random variable. You should talk to each other. Hello, welcome back. You two should talk to each other. You're okay. All right, Vanessa, what did your table come up with for a continuous random variable? So I'm assuming heart rate would be in beats per minute of which group? Humans, rats, adults, all humans? Okay. Good. Well-defined continuous random variable. Let's get another one. Nancy, what did your table come up with? Time for what? True. Boring, but true. Yes, Ishana. More specific, we like more specific, good. But you are correct, any measurement of time is something we measure that would be continuous. My second period got a little morbid and talked about the amount of blood in a human body in terms of liters. I don't know why they came back from Thanksgiving that morbid, but they did. Good. Things we measure: time, weight, distance, heart rate, age, systolic blood pressure, right? Anything you need a device to measure that can come in parts or fractions. Good. Very good. We are focused in this unit on probability for continuous random variables. We know for discrete random variables, if I wanted to find their probability distribution, I can do that with a table of x values and p of x values. Or I can do that with a histogram that shows the x values and the p of x as a height for that bar. For continuous distributions, because they can take on an infinite number of values between two endpoints, I can't use a table to do that, and I can't use a histogram really to do that. So what we use for continuous random variables to define their probability distribution is usually a density curve and a function that describes that smooth curve. Density curves model the probability distribution of a continuous random variable. So density curves do for continuous random variables what probability tables and histograms do for discrete random variables. And they follow the same rules that discrete probability distributions do, and those follow the same rules that all probability does. So there were two rules for all probability. Raise your hand if you remember one. Two rules all probabilities follow. Ooh, very good. So if I add up the probability for all of the possible outcomes in a sample space, I know they add up to 1. Good. Sum of p of x is equal to 1. What's the other one? Every probability on planet Earth has to be between which two numbers? 0 and 1. Very good. That one is super important, because I can tell you at least one of you is going to forget that at some point on the test, and a little piece of my soul is going to die. Every time you write down a probability, it should be a number between 0 and 1. Don't give me negatives. Don't give me numbers bigger than 1. Down in your face. In terms of density curves and the graph that accompanies those density curves, what that tells me is that it's always above the horizontal axis. Right? It's in the upper half of the coordinate plane. And the area under the curve is equal to 1. Because the area under the density curve represents probability. If I can spell today. Similar to the heights of those bars in a histogram representing probability. Same idea. The area under the curve between two values represents the probability that a random variable falls in that range between those values. And we have two cases for finding probability with density curves. If the density curve makes a shape that is nice and familiar and has straight edges, I can use geometry to find the area under the curve. What's the area of a rectangle? Length times width. I know that formula. Does anybody remember the formula for the area of a triangle? Very good. 1/2 base times height, or 1/2 length times width. Yeah, good. So those two formulas work for density functions that are linear or have linear sections that I can chunk them into rectangles and triangles. And we're going to tackle that one first. So we will do an example. Scoot you up here. Example says, consider the density curve for the continuous random variable x equals journey time in minutes for Selena's trip to work each day. Find the probability that Selena takes between 2 and 4 minutes to get to work. So she clearly lives next door to work. Lucky her. We want to find the probability. Takes between 2 and 4 minutes. And you'll notice they didn't give us a table. They gave us a graph. So we want to find the probability that our random variable is between 2 and 4 minutes. Yes? Did that correctly? I think so. And when I'm working with density curves, it is good practice to mark up the density curve with the relevant information from the problem. So we were told that we are looking for the probability between 2 and 4 minutes. So I'm going to mark 2 minutes on the graph. I'm going to mark 4 minutes on the graph. And to find the probability that I'm in between those two values, I need the area under that density curve. So that area that I marked in red, that's my P. That's what I'm looking for. And you guys told me that rectangles have an area of length times width. They gave us one side of that. They told us this height here is 1/3. What is the width down here? Goes from 2 to 4. What's the total width? 2. 4 minus 2 is 2. Yeah. So the area of that rectangle should be 1/3 times 2, which is 2/3, which is 0.667. I know, 667. I swear I'm not doing it on purpose. And we check, does that meet the requirement that my probability is the number between 0 and 1? Yes, you should mentally do that for every probability you calculate, please. Because I know in second semester when probabilities are nested in other things, we're going to forget, and one of you is going to give me a probability that's 1.2 something, 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 and I'm going to cry when I grade it. Good. If this were an FRQ, we would have to write a sentence. The probability that Selena takes between 2 and 4 minutes to get to work is 0.667. But good. Find the area under the curve, right? If it's geometric, nice and straight, chunk it up into rectangles and triangles, figure out the area. The question is, what if my graph is not nice and pretty like this? What do we do? Before we do that, let's name this curve. This shape is a very specific shape. This type of density curve that forms a flat line is called a uniform distribution. Not terribly common, but it does happen. Uniform distributions pop up anytime every single outcome is equally likely. So the question is, what do we do when they're not nice, pretty, and geometric? And the answer is I have to know what shape that nonlinear curve is. And we're going to focus in this unit specifically on normal. You see you smiling. Everybody loves normal curves. We talked about them before. Most common. Most of second semester is normal curves. We get normal distributions from a normally distributed random variable. They are continuous. Yay. And we've seen them before. We've seen this shape. So let's think of everything we know about a normal curve. Take about 60 seconds in your small group. What do we remember about the properties of this graph? 60 seconds. I'm going to call on some random people. What do we remember? Empirical rule, good. Properties of the normal curve. You also have access to Google if you remember nothing from Unit 1. Properties of the normal curve. What do we remember? Yes. Did you make any, Hall? Perfect. All right, Eileen, what did your table come up with? So those hash marks? Good. So those hash marks we mark by standard deviation. So to get from the mean forward, we add standard deviations to create new hash marks. Going backwards, we start at the mean, we subtract standard deviations. Good. What else? Let's see. Who else can I pick on? All right, Sophia, what did your table come up with? Very good. So the mean is equal to the median is equal to the mode, and they should all be in the same place in the middle of the graph. Because the graph is, Ivan, what did you say about that curve? It is symmetric. Very good. It is symmetric about the mean. Very good. Who else? Next victim. Chris, what else did you get? What else do you notice about that curve? Ooh, it follows the empirical rule. Very good. We're going to talk about that in a minute. I heard 2 tables come up with that. Very good. Looking at the edges of that graph, that curve gets lower and lower and lower, never quite touches the x-axis. What do we call the x-axis? Starts with an A. Asymptote. Very good. X-axis is an asymptote. Very good. We also know the total area under that curve is equal to 1 because that's the same for every density curve. Good. You will see next to the graph, there is that big, ugly equation that represents that density curve. It describes this bell shape that we see here. And that was the one nobody gave me, bell-shaped. You're not expected to remember that formula. We're not going to ask you to use it. But I know there's at least 2 people who are in AP Calculus along with AP Stats. If I want the area between 2 values under that curve, area under a curve corresponds to an integral. So you would have to integrate that big, ugly exponential function between the 2 values that you are interested in. Calculus was not a prereq for this course, so we're not going to be using calculus in here. If you want to see the nitty-gritty, you can ask me after class. We're going to use our calculator. You'll notice the next section is calculator review for a reason. Sometimes I don't need the calculator because we have the empirical rule. If the probability boundaries fall on those standard deviation hash marks, I can use what I know about the shape. We have 68% of our data within 1 standard deviation. We have 95% of our data within 2 standard deviations. We have 99.7% of our data within 3 standard deviations. It is approximate. If you used your calculator to find those, you'll notice it's not exact, it's pretty close. And sometimes it's faster to use those when your boundary values fall exactly on hash marks. Which is why it's important to draw the curve before you do the math. All right, calculator review. I trust all of my wonderful stat students have their calculator out. Nod your head yes. We are looking at a distribution, a probability distribution. So we are in the distribution menu, which is second vars. Good. We have two functions that we use for normal distributions. One of them takes boundary values, x or z, and it finds probability. Does anybody remember which function under second vars defines probability? It is normal CDF. Very good. It is always CDF and never PDF for continuous distributions. And that is because PDF represents the probability for a single value. What is the area of a straight line? 0. Yeah, we calculate area as length times width. That's a two-dimensional quality. Lines are only one dimension. They have no width, therefore they have no functional area. So we should not be using PDF for our continuous distributions. That also means that when you're writing boundary values, it doesn't matter whether you do less than or less than or equal to, because that equal to is a single straight line that has no area. Those two things are going to calculate exactly the same in terms of integrals and calculus. We don't care. So that is not going to be important. You can't mess that up on the test. Good. So normal CDF spits out probability. If I have probability and I want to know the boundary for it, which function am I using? Going backwards. I want to undo normal CDF. You all have your calculators in front of you. It's like right next to it. Frowny face. Inverse normal, yeah. Should be options 2 and 3 on your calculator under second vars. 2 is normal CDF, 3 is inverse norm. All of the density functions that we're going to look at this year have those two functions. They have a CDF function that takes in a boundary and spits out a probability. They have an inverse function that takes a probability and spits out the boundary values. Yeah, they come in pairs. These two are the most common. You need to know how to use these. A reminder before we do some examples. If this is a multiple choice question, grab your calculator, do the plug and chug, fill in the bubble on your test. If it is an FRQ, you have to do the state, plan, do, conclude thing. State, you identify everything given in the problem, you label it in words. Yeah? Plan, you tell them what you are going to do. Do as you show the work. In this case, you write out the calculator function name, you label in words all of the input. What about conclude? What goes with the conclude step? It's a favorite thing of mathematicians. We love to do it. We interpret with a sentence. Very good. You have to write a sentence. Take that number you calculated in the do step, put it in a sentence in terms of the wording in the question. What did you just find? What does it measure? What does it mean? Good. Okay. Let's do some examples. I have been talking since like 9:30 this morning. I need somebody who's got it pulled up on their Chromebook who's willing to read. Thank you, Drew.
One brand of baby bathtub comes with a dial set to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature X of the water in a randomly selected bath can be modeled by a normal probability distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. Let Y be the water temperature in degrees Fahrenheit for the randomly selected bath. Recall that degrees Fahrenheit equal 32 plus 9/5 degrees Celsius. Oh. According to one source, the temperature of a baby's bathwater should be between 9 degrees Fahrenheit and 100 degrees Fahrenheit. We are interested in finding the probability that this happens on a randomly selected day when the baby safe setting is used.
Very good. Thank you, Drew. So they threw a lot of information at us. Yeah. First thing I know after reading that is clearly this baby bathtub was made somewhere other than the US, because it's made using Celsius, and we don't use Celsius here, unfortunately. So they tell us that the temperature in the bathtub, X, is normally distributed with a mean of 34 degrees Celsius and a standard deviation. Oh, come on, pen. I'm too tired for this. There we go. 2 degrees Celsius. There we go. We do not live in a place that uses Celsius. We need to convert that to Fahrenheit. So they tell us that our new variable, Y, represents the temperature of the bathwater in Fahrenheit, and that we get Y by doing 32 plus 9/5 times the temperature in Celsius. In other words, we are doing a linear transformation on a probability distribution or continuous random variable to create a new distribution. Yay. We know those rules. We saw them right before break. They are the same for continuous that they were for discrete. So looking at this here, I'm doing two things to my random variable X. I'm adding 32, which picks up the whole curve and moves it 32 up the number line and drops it. And then I'm multiplying by 9/5, which grabs the edges and stretches outward. When I calculate the mean, whatever I do to my data, I do to my mean. So I know my mean for Y should be 32 plus 9/5 my mean for X. The shift upward is going to change that measure of center. The stretching outward is going to affect that measure of center. I need to account for both. So let's figure that out. 32 plus 9/5, and our mean for the old distribution was 34. Someone with a calculator, I want to say 93.2, but it's been a long day. I see nodding. Thank you, Jacob. Very good. So I know for my new distribution, Y, that it is normal with a mean of 93.2. What other piece of information do I need? Two things define a normal distribution, mean and standard deviation. Very good, Ashana. For standard deviation, I added a constant, so I just picked it up and slid it, and then I grabbed the edge and stretch. Which one of those two operations is going to affect the distance between the data points? The sliding or the stretching? The stretching. So I don't care that I added 32. That keeps the relative position of data and moves it all at once together. But when I grab the edges and pull, I'm spreading the data points out further. The standard deviation should increase. So I only need to worry about the multiplication part of that transformation. The addition does not play into that spread, only the multiplication. So 9/5 times 2 degrees Celsius, which is 18/5, which is 3.6. I see nodding again. Good. I'm glad my brain could still do math after a week off. This means for all of the other questions, I've now dealt with A, I don't ever have to look at X again. I am working solely in Fahrenheit. This is now the distribution for the rest of the problem. So far, so good. Okay. So part B says determine the probability that the bath water has a temperature between 90 and 100 degrees Fahrenheit on a randomly selected day when baby safe setting is used. So B says find the probability that I'm between 90 and 100. Which random variable am I finding the probability for, X or Y? Thumbs up if it's X, thumbs down if it's Y. Show me your thumbs. X or Y? X or Y? And I see some of both. Jaden, you've got a thumbs down. I agree. Why? How do you know? I'll give you a hint. It has to do with units. What were that 90 and 100 measured in? Fahrenheit or Celsius? Fahrenheit. Yeah, X was Celsius, Y was Fahrenheit. That 90 and 100 were in Fahrenheit. We're dealing with Y. Y is in Fahrenheit. Meaning I'm working here. 93.2 is my mean, 3.6 is my standard deviation. To find that, I do two things. I draw my picture, I use my calculator. You should have both pieces. So we know what a normal curve looks like. We mark the mean in the center. We go 3 hash marks out in either direction. I'm going to drop some of these down because I'm going to get crowded in here. I'm adding 3.6 going forward. I'm subtracting 3.6 going back. So 3.6, 96.8. 100.4, 104. Please, somebody check my math. See nothing. Thank you, Jacob. Going backwards, we're subtracting 3.6. So 89.6, I think. And then 80, is it 86? 86, and then 82.4. Yeah? Yeah, I can subtract in my brain. Very good. I'm going to tack on degrees Fahrenheit on that last one just to remind me. I'm going to mark the area of interest. I'm going to shade it in. I want to indicate the area under the curve that matches the probability I'm finding. So, lower bound is 90. 90 is a little bit bigger than 89.6. Right here. $100 is a little bit less than 100.4. Right here. So I'm looking for that area shaded in right there. Looking at that picture, in the graph, I have labeled two boundary values, 90 and 100. I am looking for probability. Which calculator function am I using? Normal CDF, very good. And normal CDF asks us for 4 things. Lower boundary, upper boundary, our mean, our standard deviation. Notice I am not writing symbols, I am writing them out in words. You need those word labels in order to get full credit for the do step. All right, Austin, what's my lower bound? You don't need a calculator for that part. What's my lower bound? 90, what's my upper bound? 100, very good, what's my mean? 93.2, very good, what's my standard deviation? 3.6, perfect. I'll give you a second to plug that in your calculator. I see nodding. That's a good sign. I've done this twice before. That helps. So I should get 0.784. We checked two things. One, is that between 0 and 1? Yes. 2, does it make sense in terms of what we drew in the picture? And the answer is yes. I know between 89.6 and 96.8, that's about 68% of the data. I'm just a little bit inside 1 here, but I'm just a little bit inside 2 here, meaning I am more than 68% of the data, but I'm less than 95 because that would be 2 standard on both sides. So this is between 68 and 95. I've probably done this correctly. Good. If this were the FRQ, what else would I need to do? Sentence. Very good. The probability that the water temperature will be between 90 and 100 on baby safe mode is 0.784. Yeah. But of course, they asked us one more step because we know the FRQs are brutal. Let me scroll back up. Part C says, based on our answer to part B, should a parent feel comfortable using the baby safe setting with this brand of baby bathtub? Explain your answer. So I'm going to give you about 60 seconds in your small group. Based on what we just did in part B, should a parent be worried about using the baby safe mode? Blah, 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 blah. All right, we're going to vote by table. Samuel, did your table vote safe or not safe? Not safe. Chris, did your table vote safe or not safe? Not safe. Amy, did your table vote safe or not safe? Not safe. Jennifer, safe or not safe? Not safe. Addie, safe or not safe? We have a lot of not safe. Not safe. Valeria? Not safe. I'm starting to think this is just peer pressure. Amanda? Not safe. Definitely peer pressure. You have disagreed with my last 2 classes. That's okay, as long as we can explain why. Do I have a volunteer who can tell me why they were over here in the not safe column? Yes, Drew. I'm going to check Jacob agrees in just a minute.
78.4, like that's good, but it's like it feels just a little bit, like be a bit uncertain.
So if 74 or 78.4% of temperatures are in the safe zone, how much is in the not safe zone? And that's like 21.6, yeah? Is that a similar idea what you think, Jacob? Yeah, I agree. So if the problem is telling you that safe temperatures are between 90% or 90 degrees Fahrenheit and 100% degrees Fahrenheit, if only about 3/4 are safe, there's almost a quarter that's not safe. That's 1 in 4 chances that I turn that baby safe setting on and my water is too hot for the baby or too cold for the baby. Good. My second period had a slightly different approach, which is they went to Google and looked at the actual water safe temperatures for babies, and the high was like 106, not 100, and the low was way down in the 60s. I wouldn't test this on your actual baby. But remember, this is Fahrenheit and not Celsius. So 100 is not boiling in Fahrenheit. 200 something is boiling in Fahrenheit. So 106 isn't as hot as you think it is for Fahrenheit. Good. Very good. So for those questions where it's open-ended and you're interpreting, remember that there's leeway. You just have to provide an explanation that pulled from the previous information. My third period said 3/4 of the time feels like sufficient because that area that's outside of that 3/4, most of it's pretty close to 190. There's only a little bit that's way outside of 104 and 86 something. Most of that was pretty close to 90 and 100, and they felt probably safe. So as long as you can argue, either way is fine. Good. Okay, questions on this example? No. Okay. Tomorrow, we're going to do some more examples to finish out 5A, and we will start 5B. The rest of this week is focused on 5B, which is sampling distributions. We're probably not going to finish Unit 5 before finals week, and that's okay. We'll finish when you get back from break because you don't have a final exam. Reminders. There is homework that follows up these notes. You have enough information to do it, but we will do a couple more examples to help solidify tomorrow. Tomorrow, Unit 4 test goes live if you want to do test corrections. You've got till next Friday at 5 p.m. for late work. Please use the last 10 minutes of class wisely. Yay!